시작해. Hi, my name is Hyunsung Eric Cho from KGSEA Math Circle. I'll be talking about origami. So, what is origami? It is the art of paper folding. So, you might think that there's not a lot of interesting things about origami, but I'll prove you guys wrong today. So origami, you guys all know these little figures that you guys have made when you guys were little. There's a lot of cool things that you can do with origami. First, let's try this activity where you construct the biggest equilateral triangle possible using origami on that piece of paper. I'll give you guys like 1 or 2 minutes. Oh yeah, if you guys need more paper, it's just up here. Sorry for the people at home though. You guys might not have this type of square piece of paper, but I guess you guys can just follow along the video when you get these types of paper. Okay, should we try going over the actual solution to this problem? Oh, people who are watching the video, you guys can just stop the video and try exploring more ways. Okay, anyway, we'll go to the first step. So first, fold the paper in half vertically and horizontally. I'll do this with you guys so you guys can see. This is folding it vertically in half, right? Then you guys can fold it horizontally in half. Yes. Okay, you guys just want to crease that out a little. Okay. And then step 2. This is like the important one. You want to fold the left corner to the center vertical line while making sure that it only folds once in the corner, as you can see in the picture. But you just need to do that on one side of the paper. It might be a little hard in the beginning, but push through it. I know you guys can do it. Okay. Okay, seeing that everyone has already done that, we'll go to the next step, which is to fold the bottom right corner to the center horizontal line, as you can see in the picture. Yes. Amazing. You guys see what is happening. And then you want to fold the vertical, the dotted line in the image that you can see on the screen, right? Oh my God, you guys made an equilateral triangle. That is absolutely sensational. There's other things that you can do using origami as well. This equilateral triangle, if one side length of the paper, the square piece of paper was considered 1, then the side length of the triangle would be 2 over root 2 plus root 3. You guys can try doing this by just putting a length on there, and it's pretty easy, but we'll move on due to time constraints. Okay, the next problem. Can you trisect an angle using origami? You cannot do this problem using compass and straight edge, but can you do it using origami? I really wonder. So the first step, to make it easy on you guys will first create an angle theta by folding along that line that you see on the screen right now. And that angle theta will be the angle that you're trying to trisect. I'll give you guys like 2 more minutes or 1. Never mind, I'll just give you guys 10 more seconds. Seeing that no one is really close. Okay, so step 2 would be to create a horizontal crease, as you can see in 1. I usually just do this as the half line, like the horizontal half line, but you want to unfold the first fold that you did, and then you want to create the half line. Okay, and then you want to fold the bottom half of the half again in half, if that made sense. Yes. It's also easier for the people who are watching the video to actually draw out the lines using pen or something for the next step. But assuming that you guys already done this, we'll go to the next step. So the next step is actually a pretty hard step. You'll see that there's a point P2 on the screen. You want that point to go to L2, and you want P1 to go to L1 at the same time. You might need some adjusting to do this. But once you got it, just crease it down. You guys got it? Okay. So the next step would be, you would see that there's this crease of L1 left on your that triangle part that you folded down. You want to follow along that crease. Yes. And you will get L3. Okay, next step. So you want to fold from the bottom to L3. So you want to basically bisect that angle. Am I going too fast? A little? Okay, my bad. Okay. Now, I don't know if you people can see it, but you have already trisected the angle theta. So there's actually a proof for this. It is using congruent triangles between triangle ABP1 and CBP1, and also the congruent triangles between DCP1 and CBP1. Due to time constraints, I won't be explaining it, but you guys can see the proof on the screen right now. Okay, next, we'll be going into the basics of origami. Origami is consisted of multiple folds called the valley fold, mountain fold. There are also other folds, but we'll keep it to the basics right now. So I'll be explaining to you guys how to fold the Murray Ori fold. Okay, this is going to be slightly complicated. So first, you want to fold the paper horizontally into 6 equal pieces. You might want to do this using a ruler for the best results, but we'll eyeball it for now. And just in case you guys want to see the Murray Ori fold actually built in real life, I'll be passing these around. Okay. What you want to do, you want to fold these 6 parts in alternating mountain and valley folds. So in the end, from the side view, it would look like this piece of paper. Okay. Just crease that out a little, and we'll move on to the next step. The next step is somewhat complicated. Starting from one side of the strip, we'll be folding slightly inwards. Doesn't matter what angle for right now, but you will be folding it like this. Okay. And then you would flip that paper. You would fold it the same way, making sure that the top line is parallel to the other top line. You want to do this to the best of your ability. For the best results, make sure that this point is on the other side. Like this. Okay, and you want to repeat that process until you go through the whole strap. Yes, like that, Lim. So that in the end, you would actually have two parallel lines on both sides. This will take a little bit. Seeing that people are struggling a little bit, maybe you guys can watch over the video again later and try it by yourselves. But yes, we'll be moving on to the next step. Next, we will be unfolding everything that you have done into the paper and just be looking at the creases. Your paper will be consisted of horizontal lines and also zigzag lines going. You would have vertical lines and zigzag horizontal lines. For the zigzag horizontal lines, you want to be folding them in alternating creases. So the first zigzag line, you would want to do them in mountain folds. The second one, you want to do them in valley folds. And we'll just be zooming through that step right now. But you guys can try it out when you guys get home. So there are many, okay, you guys can pass this around too. There are many different properties of the Miura Ori fold. It's the tessellation of parallelograms, and when the paper is unfolded, you can actually see that it's a pattern of parallelograms, and the angle and dimension of the parallelograms determines the shape of this tessellation. It also has this thing called 1 degree of freedom, which means the whole structure can be opened and closed through a single motion. And it also follows the Kawasaki theorem, which says like the crease pattern is folded flat if and only if there's the alternating sum and differences of the angles add up to 0. As you can see, it's made of 4 rhombi. So it follows this Kawasaki theorem. In this diagram on the left, you would see that alpha and delta is the same size, and beta and gamma is the same size. So it follows this theorem. There are different properties. There are more different properties, such as the high stiffness. It can hold up heavy devices, and it is caused by the pop-through defects from between the parallelograms. Okay. I'll have to borrow this now. But you can see that this piece of thing can actually hold up my computer very well. It can hold up at home the weight of 10 computers, and that there's one that's going through right now made out of paper. Yes, that one can hold up to 3 computers. We tried. Anyway, it can hold up very heavy weights. It also has a negative Poisson ratio, which I'll demonstrate. The Poisson ratio is the idea that when something is strained one way, it will expand in another way. So as you can see in this mask, when you pull, it gets shorter this way, but it gets longer this way. And then if you pull it the other way, it would get shorter the other way. This is positive Poisson ratio. But if you try playing around with the Murray-Ori fold, you would see that it has a negative Poisson ratio. So when you contract it in one way, it would actually contract in the other way as well. Very strange object. There's also biomimicry of Murray-Ori fold. You would see this in leaves, and different leaves would have the valley and mountain pattern of the Murray-Ori fold. There's different applications of the Murray-Ori fold, and my personal favorite is how they used it in solar panels to optimize the folding mechanisms. They use this to minimize the space that the solar panels take up when they launch it into space. And Space Flyer Unit in 1996 was the first to use this technology. They were made by Japan. There are different applications, such as using them in maps and in batteries, where they actually need it as compact as possible. It's also used in lab tools and experiments, such as gas pressure sheets. It also helps to create a cellular metamaterial from the layers of these folds. If you actually have multiple of these Murray-Ori folds, you can actually combine them together. Yes. There are also much more applications of the Murray-Ori fold, as you can see here. So how is origami being used in our lives? Well, they use it in medical tools to make smaller medical tools and even smaller medicine. It is also used in agricultural structures, and automobile companies are using it to design airbags. Aerospace companies plan to build foldable wings, micro and nano structures for drug delivery inside your body, and like micro robotics. And this image is a cool thing that I found out about like a month ago. It's Harvard engineers created a robot that folds itself and moves around without any human intervention, and it uses heat between the ridges to activate the mountain and valley folds. And it was just something cool that I wanted to share with you people. Anyway, to recap, origami can help us solve mathematical problems that we were not able to solve before.